In this video, I'm going to explain Buffon's needle experiment to approximate pi. It's an interesting use of probability, and I first learned about it when I was in 7th grade. The math teacher had us drop little needles on the floor and use it to approximate pi. The approximation wasn't very good. And what does it have to do with pi, and what is the experiment? Okay, so the idea is, let's say that you have a floor with tiles of width 1. So you have this floor, there's square tiles of width 1. So just imagine a floor with these square tiles of width 1, and suppose that you have a needle of length L, which is less than or equal to 1, and you drop it on the floor. So your needle might be like this, or it might be like this, or it might be like this, or this, or this. I mean, you have all sorts of possibilities for the needle. And the question is, what's the probability that the needle touches one of the cracks? So it's this, you imagine it's this infinite floor. Okay. We assume that the needle and the cracks have width 0, of course. So to solve this, we're going to let x be the distance from the center of the needle to the nearest crack. Okay. And we'll let theta be the angle between 0 and pi. So I'm using the notation, right? It's an element of the set from 0 to pi. It's the angle that the top half of the needle makes with the crack. And we assume that the ways the needle can land are equally likely. So x can go from 0 to a half. Why can x go from 0 to a half? Well, because if you have a tile and it has length 1, then so we're letting x be the distance from the center of the needle to the nearest crack. So the center, so if the center is on the crack, then your x would be 0, but then the biggest possible value of the center to the crack, the distance from the center to the crack is a half, right? That's if the center is kind of in the middle and the needle is like this. So x goes from 0 to a half, and theta, well, theta is something that can go from 0 to pi. And we assume that each of these possibilities is equally likely. So what that means is that the joint distribution is uniform. So the area of this is half pi, and so you assume, in other words, that the joint distribution, of x theta is f of little x little theta is 2 over pi if x is in this region, from 0 to a half, and theta is between 0 and pi, and 0 otherwise. Actually, theta, since L is, let's see, did I assume? Yeah, L could be 1. So yeah, x could be a half. Okay. So that's the joint density. And now, when does the needle touch the crack? Well, here's the picture. So here's the floor, and if you have the needle, okay, so you have the needle like this, and then the center is here, and we let x be the distance, the smallest distance, the distance from the center of the needle to the crack. Then what's going on? Well, where is theta? Theta is here. So this length of the needle is L, and so you have a length of L over 2 here and a length of L over 2 here. And so this vertical distance here is L over 2 sine theta. Right? L over 2 times sine of theta, because you have this triangle, like if you look at this triangle here, and this length is L over 2, then the coordinates, see, this length will be L over 2 cosine theta, or the absolute value, and then this length will be L over 2 sine theta. So the needle touches the crack precisely when x is less than or equal to L over 2 times sine of theta. So we want to look at, in this region, this is the region of possible outcomes. You want to see where x is less than or equal to L over 2 sine theta. So we let, say, capital A be the sort of successful region, right? It's x and theta in this rectangle such that x is less than or equal to L over 2 times sine of theta. Okay, and so to figure out the probability that we want, we have to integrate over this region A. And so the probability that the needle touches a crack is the integral of the joint density function over a, so that's 2 over pi dx d theta. And how do we set up the integral? Well, x is going to go from 0 to L over 2 sine theta, and theta will go from 0 to pi. So we're doing this integral like this. And so that's just going to give us the integral from 0 to pi of 2 over pi times L over 2 sine theta d theta. So that's going to be L over pi times the integral of sine theta from 0 to pi. And so that's going to be L over pi times negative cosine of pi minus negative cosine of 0. And that's going to give us, let's see, cosine of pi is negative 1. So you're going to get 1 plus 1, which is 2. So 2L over pi. So if, in particular, so that's the answer. It's 2L over pi. That's the probability that you touch the crack. So in particular, if you take L to be a half, then the probability of touching the crack is 1 over pi. Not L over pi. What am I saying? 1 over pi. So what you could do, and what Buffon did, was you can perform the experiment lots and lots of times and then figure out 1 over the fraction of times the needle hit the crack. And that would give you an approximation of pi. It turns out, though, that the approximations you get are not very good, and you would need something like 100 million tosses to get a decent approximation of pi. So if you do the approximation 10,000 times, you might get something like 3.1 or something like that, but or 3.2, 3.0, but you wouldn't get something that close to pi. But it's still interesting, and if you do it enough times, you should get a better approximation of pi. So that's Buffon's needle experiment, and also the explanation behind the theory of why this would give an approximation of pi.